Hello, everyone. Today we're going to talk a little bit about objects that are in free fall. Okay. There is a question here that if I'm standing on top of the Empire State Building, and if I drop a feather and a bowling ball from the exact same height at the exact same time, which one hits the ground first? Take a minute, think about that, and then you can go ahead and go on to the next slide. There's a video here that I would like you guys to watch. Actually, this is going to end up being in a Edpuzzle video for you guys to complete and watch. So you don't have to actually watch it in the notes. This will be its own little separate assignment. Free fall acceleration. Objects that are in free fall. That means that they are under the influence of gravity only. There is not anything else that is pulling or affecting how they are traveling down towards the Earth's surface. Objects always accelerate downward towards the ground, towards the center of the Earth. Gravity doesn't pull something sideways. It's always going to be directed straight down towards the center of the Earth. And since it's accelerating, that means that it's going to constantly be changing its speed or maybe even its direction, depending on which way it happens to be moving at the start. The acceleration of gravity is always 10 meters per second squared here on Earth. That will always be true. It will fluctuate a little bit, but not enough that will actually change our values for what we're using in here. Whenever it's talking about maybe acceleration of gravity and how it can change, it might only be like a couple decimal points, but we're talking about thousands and thousands of meters that it has to go in order for this to actually have some negligible change. But for all intents and purposes, for our consideration, anytime we're using acceleration of gravity, g, that is going to be 10 meters per second squared here on Earth. And that is true for different locations. If I were to go to the moon, the acceleration of gravity is much less. That's why it appears like astronauts are bouncing. It's because the acceleration takes a long time to slow them down. And then as they're coming back down, it takes a lot longer for them to speed back up. If I go to Mars, the acceleration of gravity is only about 3.7. If I go to something that's bigger, like on Jupiter, the acceleration of gravity is actually about 26, almost 27 meters per second squared. So a lot bigger. But here on Earth, our value is right around 10. It is constant for all falling objects. It doesn't matter what object it is, if it's a tiny paperclip or if it is a big, heavy tank shell. If I let them go, they fall exactly the same, just like you saw in the video that you were supposed to have watched on your first assignment. Okay, free fall accelerations. How can all objects fall at the same rate? So if they're all going to accelerate the same speed, why is it they don't always land at the same time? Well, here on Earth, we can't just ignore air resistance. It's something that's always going to be present. The only way that we can ignore it is if we were actually go inside of like one of those big tubes, like in the video, where they suck out all the air and create a vacuum. Air resistance, kind of think of how a parachute works. The bigger surface area, the more area there is to catch the wind, the air, the more force it's going to be there to slow you down. Now, the math ends up being very, very difficult once you start considering air resistance. And believe me, I didn't even have that until maybe my third, probably actually more like my sixth physics class. So nothing that we're going to do in here with air resistance, we will always go through and ignore it. So keep that in mind. If I'm dropping a feather and a brick from the same height at the exact time, which one will land first without air resistance? Think back to the second half of the video after they sucked out all the air. Now, you might have heard the myth that if you drop a penny from the top of the Empire State Building, which is very, very tall, in fact, height, it's about 12,500 feet or 444 or 443 meters. So very, very large and a lot of room for it to actually fall down. Now, while I do have that penny, and if it's accelerating for that time, it doesn't actually accelerate the entire time as it's falling because there is air that's going to slow it down. That is, it'll actually increase its speed until it reaches a point called terminal velocity. Terminal velocity is the point which it doesn't accelerate anymore. It just kind of falls at the same speed. Think about as you're driving down a highway in your car. You know, if you're going on I-99 and going 70 mile an hour, you can't just let off the gas pedal. If you let off the gas pedal, your car is eventually going to slow down because it's getting a lot of air resistance from what you're traveling. Well, same thing. You have to keep that gas going forward. Gravity's pulling you down. There's air resistance that's pulling you backwards. Eventually, those two forces will cancel each other out. And what you're left with is just something falling with a constant speed. And that's what we call terminal velocity. That is the maximum speed that an object can reach while in free fall. That occurs when gravity pulling down equals the air resistance pushing back up. And if there's no acceleration, that means we're going to fall at a constant speed. Now, if you ever happen to go skydiving, skydivers don't accelerate the entire time to the ground. They will reach their own top speed or terminal velocity. Now, you can adjust your terminal velocity a little bit by positioning your body to where you catch more or less drag. If you kind of end up having a stable belly to earth position, stable skydiving position. That's where you see them kind of flowing down. They appear like they're on their stomachs. They'll look something like this. But that increases the surface area where they're catching the wind, and that ends up trying to help them slow down. If they're in a stable head down position, they can reach almost double their speed of going about 240 to 290 kilometers per hour, about 150, 180 miles per hour. And further minimization of drag, maybe they're having special suits, maybe they're trying to make themselves super, super tiny, but that can allow them to reach even faster speeds all the way up to maybe 300 miles per hour. Now, whenever people go out skydiving, they have records. People try to beat each other. In fact, there was his name. He did Red Bull. Felix Baumgartner. He went through back in the early 2010s, I think it was. He jumped out of a big balloon, and he ended up going through, and he ended up setting a record for the largest free fall. He went over 700 miles per hour. In 2014, Alan Eustace ended up leaping from a balloon that was a little bit higher, and he actually went over 843 miles per hour before the air started to get thick and started to slow him down by basically going through like a different medium. Think about how easy it is to have your hand out the window versus having your hand going through water. There's a difference between having thin air in the upper atmosphere where he wasn't slowed down by the air. But whenever he entered back in the atmosphere where there was air, that slowed him down to a much more manageable speed. And here's a little video clip that you guys can watch Felix jump out. It's pretty intense. He falls for over 4 minutes. 4 minutes just falling straight down towards the ground. Ridiculous. Now, we go through, we do a couple calculations, but basically we are just modifying equations we've already known and we've already used. G is just a specific acceleration. This actually comes from the equation V equals A times T, whenever I have something times rest. And G all the time is always going to be 10 meters per second squared. So let's go ahead and go over and we'll do the two examples here. If I'm solving for the speed which a flower pot is moving after falling for 5 seconds, they're giving me the time of 5 seconds. They want to know what is the speed. That is the only bit of information that they gave us, but we're going to be using this equation every single time. It doesn't tell us what G is, but we need to know, hey, there's a flower pot. The only place in the solar system I know that there is a flower pot is on Earth, where Earth, the acceleration of gravity is 10 meters per second squared. This will always be 10. So V equals 10. There's no symbol here between those two variables. That means it's multiplication. So I'm going to take 10 multiplied by 5, and they're giving me a velocity of 50 meters per second. And there's example number 1. Ends up being a pretty easy equation. Number 2, a ball is falling for 7 seconds. Seconds measures time. How fast is it going when it hits the ground? Well, V is G times T. Oh, I didn't put G in my data table. G is always 10 meters per second squared. So when I plug in 10, this time I'm multiplying by 7 seconds. My final velocity is going to be 70 meters per second. Solving for the speed, pretty simple. Basically, we're just multiplying each number by 10 because that's what the acceleration of gravity is. So that means if I drop something, if it takes 7 seconds to land, it's going to be moving 70 meters per second. Every single second, it increases its speed by 10 meters per second. That is that acceleration. All right, so that was the easy one. Let's take a look here at our next one. The time it takes for an object to fall depends on only the height at which the object is above the ground. To solve for the time, we take the square roots, and everything is inside of the square root. That means that, honestly, what you're probably better off doing, do everything inside the square roots, get that number in your calculator, and then take the square root of that number. Now let's go ahead and go over the example problems. A bowling ball falls from a height of 45 meters. That is my distance that it's falling. D is 45 m. How long does it take to hit the ground? How long does it take? That's asking me to solve for time. They don't give it to me. But again, every single time I do free fall problems, G is 10 meters per second squared. I'm going to write down my equation. T equals square root 2D divided by G. Plugging in my numbers. 2, 45 divided by 10. Like I said, you guys can simplify everything underneath the square root. 2 times 45. And again, and I get this question all the time with kids that are sitting here in the room with me. How do I put a fraction in a calculator that doesn't have a fraction button? A fraction means divide. So I'm taking 2 times 45. I'm dividing by 10. So that's giving me a number, square root 9. And then this is what I want to type in and take the square root of. They're giving me that means that the object is going to take 3 seconds to fall 49 meters. That's how long it takes. Example number 2, a golf ball, which is smaller than a bowling ball, falls from a height of 45 meters. D equals 45 m. G, always 10 meters per second squared. Again, that's acceleration. How long does it take? Solving for T. T equals square root 2D divided by G. Square root 2, 45, divide by 10. Again, I go through, do this in the calculator. I want to take the square root of 9, which guess what? That was the same numbers we just had. The time is still 3 seconds. How did I get 3 seconds? I took the square root of 9. 9 square root. Depending on your calculator, why did I divide by 10? 9 square root. And that's going to give me 3 seconds as my answer. It doesn't matter the size of an object. All objects fall at the same rate. All of them are going to be there by 10. But just my recommendation, do everything underneath the square root first, then take the square root with this equation. Particularly as I don't know necessarily what calculator you guys might use. if you're using the calculator in Google, or maybe you have your cell phone that you're using too. Okay. One last thing that we can solve for, maybe we measure the time, but we want to know how far is a hole, or how long did it take or how far did it fall if it fell for this particular amount of time? Well, this was just that same equation we were using, D equals 0.5 AT squared. This is the same equation, only now instead of A, I'm putting G there because it's just a specific acceleration. We're just still doing acceleration problems. Now, if it says a rock falls from the top of a cliff, it takes 5 seconds to reach the ground. How high is the cliff? They're giving me a time, 5 seconds. It's an object that is in the air, so I know the acceleration is 10 meters per second squared. But if it's asking how high or how far, they're asking for distance. I want to write my equation down. Distance equals 0.5 gt squared. D equals 0.5. G is 10. Time is 5. Only the time gets squared. And I can type that in a calculator just like it is. Even if you don't like having the parentheses, you can do multiplication between those numbers. 0.5 times 10 times 5 squared. Do not press equals before pressing the square button. The distance is 125 meters. If I use the parentheses, pretty much, If I use the parentheses, I'll get the same answer. 0.5. There, 0.5 times 10 and 5 squared. And I still get 125 if I'm using parentheses instead of using the multiplication button. Okay. One last problem. A kid drops a toy out of the bedroom window. It takes 2 seconds to hit the ground. That is a measurement of time. It's falling. I know what the acceleration of gravity is on Earth. That is 10 meters per second squared. How high is the bedroom? That's solving for a distance. I'm going to write my equation down. D equals 0.5 gt squared. I'm going to plug in to the equation. And then I'm going to type in my calculator. 0.5 times 10 times 2 squared. And the distance here is 20 meters. And that's it. And that should be, I believe, the end of your notes. Yep, that's it. End of video. All right. Good luck this week, guys.